Hi. I tried to compile one of my old programs without the C runtime, just to see what it would take to get it done. And I immediately hit a roadblock that I wasn't expecting, and that has to do with command line arguments. In a typical C application, the main function passes in command line arguments for me to use, but without the C runtime libraries linked into my program, I do not have these parameters available. So I was wondering what to do, and I went into a bit of a rabbit hole about command line arguments. And I would like to show you what I learned and how I'm going to handle command line arguments in my own programs going forward. But I have to preface that what I'm showing here is Windows only. Linux and other operating systems might be handling these things differently, but I have no way of knowing because Windows is my main development platform at this time. I also tried to split this video into chapters, so the rough outline is this. First, I'm going to take a look on how command line arguments are handled in a typical C application. Then I'm going to take a look at how a native Windows application handles command line arguments. I will then be taking a look under the hood of the Windows C runtime to see what exactly it is doing to handle command line arguments. And next I will try to replicate the same thing for my own program that does not use the C runtime library. And in the end, I'm going to show you my preferred way of handling command line arguments. So let's start with the typical C application and how to access command line arguments there. So here I have a typical C application with a main function that has two parameters. The first one is called argc, which stands for argument count. And this will essentially be just the number of command line arguments that have been passed into this executable. So I'm now just going to print out that number with printf, and let's compile and run this and see what it spits out. So let's say I pass in A, B, C. Every command line arguments is separated by a white space character. So I would expect 3 command line arguments, but the number for some reason it prints out is 4. Now we'll see in a second why if we take a look at the next parameter of the main function, which is argv, which is an array of char pointers. So argv will essentially hold all the command line arguments that I pass into the program. We can figure out what's going on by printing out the contents of what is stored in the argv array. For that, I can just introduce a for loop and then print out every single argument based on the index out to the array. So because argc is 4, I would now expect 4 arguments being printed out onto the console. And as you can see, it prints out indeed 4 of these arguments, and we have A, B, and C down here, which is what we expect. But then we can also see the name of the executable that is being run right now. So the first argument in the argv array is always going to be the name of the current executable that I'm running. Argv does not only hold 4 items in the array, but actually 5, though the last one is just a null pointer essentially. So you could actually iterate through the array without the need of argc. For example, I could replace this whole for loop here with a while loop, where I'm just increasing the pointer, and at some point it will reach 0 and just stop. But let's say I do not want to check command line arguments within the main function. Let's say I have another function, something like void something. So how can I pass command line arguments in a separate function like this? It might be in a different C file maybe, or a different header file. So do I actually have to propagate these arguments throughout every single call up to the point of where I have my code that is passing the command line arguments? Or is there a different way of doing things? Well, luckily in the C runtime, argc and argv are also defined as global variables that I can use throughout my whole program. So in here, in this function something, if I wanted to print out argc, I can just call __argc, and it is exactly the same. And I can also do the same for argv. So if I want to iterate through argv, I can just access the global __argv variable. Now, I've mentioned before how command line arguments are separated by a whitespace, but there are actually a few more rules involved when it comes to command line parsing. So let me show you. Now let's look at an example of how command line arguments are parsed within the C library. Let's take this command line argument string that we're having right here, and we'll start from left to right. And the first argument is always going to be the path and name of the executable. It might be surrounded by quotation marks, or it might not be. In our case, it has quotation marks, and this will be put into the first slot of the argv array. As you can see, the surrounding quotation marks are being removed, but otherwise it's just going to be one-to-one the same text. Then after each space, a new argument begins, and in this case we just have a single character argument called a, so we're going to put that as the second item in the argv array. Then after that white space, it's followed by a 3-character argument called foo, so we're going to put that into the third slot of the argv array. And then the last argument is a quoted argument. This is where the special rules come in. So this would be put into the fourth slot of the argv array, but I just want to talk about how this actually is parsed, because this is not going to be one-to-one the same text. So let's start from left to right again. First, we're noting that this is a quoted argument. Now, on quoted arguments, similar as with the executable name, the quotation marks actually do not appear in the final value, so this is going to be removed. Now, a quoted argument actually treats white spaces just as another part of text that needs to be copied into the final value. After the word quoted, that white space will not indicate the start of a new argument, but instead it will just be part of the value. Any backslash that is followed by a quotation mark is actually interpreted as an escaped quotation mark character. Usually we would look for an end quotation mark, and you would see this quotation mark right here, and you would think, oh yeah, so this is the end of our quoted argument. But it is not, because it is actually prefaced with a backslash. Now, this will also not be put like this into the final value. Every time we have a backslash followed by a quotation mark, it will just be replaced by a single quotation mark character. Then, any number of backslashes that are followed by a quotation mark will be parsed in a special way as well. First, what's going to happen is the C runtime is going to count the number of backslashes before that quotation mark. In this instance, it's 3, which means this is an uneven number of backslashes. Since it's uneven, there's a special rule in place where every pair of backslashes will be replaced by a single backslash, and the last remaining backslash with a quotation mark will be interpreted as an escaped quotation mark character. So what we end up with is actually just a single backslash and a quotation mark character. Now, any other number of backslashes that are not followed by a quotation mark will just be copied as is. And then we have the last 2 backslashes followed by a quotation mark. Now, this is now an even number of backslashes, which means every pair of backslashes will just be replaced by a single backslash, and the last quotation mark will be interpreted as the start or end of a quoted argument. So in our case, it will be interpreted as the end of the quoted argument, and what we'll end up with is just a single backslash in our final value. Now, this is the whole string parsed, and there's one last item missing, and that is the 5th item in the argv array, which will be just a null pointer to indicate that this array is done. Now, there's a few more minor rules, but I'm not going to go too deep into this, and I'm also not going to cover wildcard expansions because I personally never used them, and I didn't want to blow up this video too much, so I'm not going to deal with wildcard expansions at all throughout this video. So that is how command line arguments work in a typical C application. But what about a native Windows application? So what I have here is a typical Windows application that is using the win_main entry point as opposed to just main. And there is a bunch of parameters here, but as you can see, it does have no argc or argv available anywhere. What it does have, however, is this white string pointer called command line. So let's see what this has and print it out to the console. I'm just getting the standard output handle here and just simply writing the command line string out into the console. So if I run this with my little start script, it will also pass in the ABC command line arguments, the same as I have done with the C application. And as you can see, it actually prints out A, B, and C. However, as you might notice, there is no name of the executable anywhere in that string. So what's being passed into the win main is actually just all the command line arguments without the executable name. There is, however, a way to get the whole command line argument string that also includes the path and name of the executable, and that is by calling get command line. In this instance, I'm calling the white character version, so I have a wchrt right here, and if I print this one out onto the console instead, we can see that I now get the string which includes the executable name as well as all the command line arguments. But what if I actually would like to have argc and argv similar to a C application in a native Windows application? Well, there is a function I can call which is called command line to argvw. There I can pass in the command line argument string, and it will return me the argument count, as well as a pointer of white string characters, which is basically the argv array. This function also follows the same parsing rules as the C runtime. However, in order for this function to work, I also have to link against the shell32 lib, because this function actually lives in the shell32 DLL. I also need to include the shell API header right here. And now that I have argc and argv, I can just have a little for loop right here and then just print out whatever is at the specified index here in the argv array. And if I run this now, you can see that I now emulated the same behavior as I had in my C application. So I have argument 0 here, which is the executable name, and then argument 1, 2, and 3, which is A, B, and C respectively. As you can see, handling command line arguments between a native Windows application and a C application is a bit different. And if I wanted to handle command line arguments in a program that does not link to the C runtime, I could just use the Windows APIs that I just showed. But that comes with a few trade-offs. For one, I have to link to shell32, which is another dependency that I have to maintain and ship, and then it only works on white character strings, essentially UTF-16. But if my application has set the process code page to UTF-8, then I have to go through the extra steps of converting UTF-8 to UTF-16. I would like to avoid all of this if possible, but what am I supposed to do? Well, the first thing I thought of was to have a look at the C Runtime Source Code to see how it translates the Windows way of handling command line arguments into what a C programmer would expect. Maybe there's a few API calls that I didn't know about or something like that. So let's have a look. So the first thing I did was try to track down the argc and argv global variables, and I found them in argv_data.cpp. as you can see right here. And what we can also find down here is the A command line and W command line variables, which is essentially the raw command line as a narrow or wide string. So this would suggest that the C runtime is basically also receiving the raw command line string and then doing some extra work to populate argc and argv. And if we scroll down a little bit, we can see the acrt initialize command line function right here, where A command line and W command line actually get populated. And as you can see, they just call out into the native Windows API functions get command line A and get command line W. So that would suggest that any process on Windows just receives the command line arguments as a full string. And if we now have a look in the argv_parsing.cpp file, we can actually see that there's this common configure argv function right here, which basically says read the command line and create the argv array for C programs. So this is where the whole parsing of the arguments takes place. And there's a bunch of stuff happening. There's also some code paths for wildcard expansion, which, as I mentioned before, I'm completely going to ignore in this video because that's a bit out of scope. And as you can see, the first thing it's doing, it's just calls get command line, which is a function that is defined further up in the file. And all it's doing is returning the raw command line string that we have initialized before. Then it goes on to call a function called parse command line, where it passes in the raw command line. It has two arguments that are being set to null, but what it then returns is the argument count and the character count. So the argument count essentially being argc, and the character count being the number of bytes that are needed for all command line arguments after parsing. It then allocates a buffer for all the command line arguments. I will go into a bit more detail on how this buffer allocation works later on in the video. For now, let's just continue. Then it calls the same parse command line function again, the same as up here, but this time instead of null pointers, it has first argument filled in and first string as well. It then again returns argument count and character count, although that's probably not really needed. And then because we're not expanding wildcards, we are essentially done. As you can see, argc gets set, and then we have argv right here. So this is what would happen in a typical C application. But what about a native Windows application? Well, even a typical Windows application includes the C runtime, and we can see that by having a look at the argv_winmain.cpp file. There again, we have a get command line function that just returns the raw command line that we have read before. And then further down, we can see it does some parsing where it essentially just skips the executable name in the beginning. As you remember, if we looked at the p command line argument that's being passed into winmain, it didn't include the executable name. So what I learned is that the C runtime relies on the same get command line call I have used in the native Windows application. It then iterates over the return string twice, one time to count all the arguments, and the second time to copy all arguments into a newly allocated buffer. So there's a lot of extra work involved to populate argv and argc for a typical C application. The Windows Shell 32 command line to argv function is presumably doing the exact same thing. I cannot confirm that, however, because I do not have access to the source code. To my knowledge, it's not publicly available anywhere. Anyways, now that I know what is going on under the hood, I can try to replicate this for my own program that does not use the C runtime libraries. Here I have an example application that does not link to the C runtime libraries, and instead of a main function, I have this program start function right here. I'm getting the command line A string right here. I'm printing it out onto the console, and then I call parse command line, which is my own implementation of what the C runtime is doing. It has the exact same parameters, so it has the command line it accepts, a pointer to argv, argbase, argc, and count. So I'm calling it first to count all the arguments and populate the argc variable. It will also populate the character count, so it counts the amount of bytes it will need for the buffer to allocate after all the arguments have been parsed. And after I counted the arguments and the characters, I'm going to allocate a new buffer on the heap right here. I will explain in detail how this works in a second. And then there is the second call to parse command line, now with argv and the first value populated. And then I'm just going to iterate with this for loop over every argument and print out everything that's stored in argv. And I can show you real quick that it works by just running it. Now the arguments it passes in is quite long. It includes a lot of backslashes and a quotation mark because I had to make sure that the parsing actually works. We print out the argument count, the character count that is needed, how many bytes are being allocated, and then it prints out all the arguments. So now, before I dive into the implementation of the command line parsing, let me talk about the buffer allocation. So let's just assume we have a block of memory right here, and I need to figure out how much to allocate for the argv array. So let's assume argc is 3. So we now know we have 3 command line arguments that we need to store in our argv array. And then the character count is 42 bytes. So to get the overall size of the buffer, there's a simple formula, which is just the argument count +1. Now the +1 is because of the null termination character times size of the pointer. Now I need to use the size of the pointer on this machine because the argv array is essentially just a sequence of pointers. And those pointers point to some other memory location where the string is stored. So in this instance, space for argv would be argc +1 times 2, which is, 3 + 1 is 4, times 2 will be 8. So I will need 8 bytes of memory for the argv array. Now I went with a size of pointers of 2 bytes here, but realistically on a modern machine it will probably be 8 bytes for the pointers, but this is just for simplicity for this diagram. The first 8 bytes of our memory block should be reserved for the argv array. But now we also need space for all the characters of the command line arguments. Where do we store those? Well, an array needs to be contiguous, so argv can't just have any gaps in between. So the most logical step would be to copy all the characters of all arguments after the last element of argv. So essentially the first argument would go right here, and then we have a bigger second argument that can come in right after that, and then our last argument is a bit shorter and it will just occupy this much space right here. The total byte count we have to actually allocate on the heap is 50. But now all the elements in the argv array need to point to the start of the actual argument. So the first element has to point to address 1008 here, which is the start of the first argument. Then the second item in the array has to point to the start of the second argument, in this case address 1015. And then of course the third argument needs to point to its start, which is address 102C. And then we just need space for the last item in the array, which will just be the null pointer. Even though it is a null pointer, nonetheless it takes exactly the same amount of space as any other pointer would. I would now like to show you my parse command line implementation. So let's take, for example, we have this command line argument string. So we have a quoted executable, and then we have 2 command line arguments. This base pointer right here is pointing to the first character in the command line argument string. So in this case, the quotation mark. Here on the side, I'm gonna have the argv array. And argv is pointing to the first item of the array, which you remember is just a char pointer. The other argument here is argbase, which is essentially just the pointer to the newly allocated memory where I need to copy all the characters into. At the moment, it's pointing to some arbitrary address, which I called 0A. It is basically the first available byte where I can copy characters into after all the argv pointers. Then I have argc, which is essentially just the argument count, and I'm gonna set that to 1 because I know there always will be an executable name in there, so I'm just going to set it to 1 immediately. And then count right here is the amount of characters that needs to be copied into the newly allocated array. Now at the moment this will be 0. So if you remember, you need to call this function twice, because first you're going through with counting without copying any characters, then you allocate the buffer for argv and the argbase, and then you essentially call this function again to copy all the characters. Now what I'm showcasing here is basically everything combined into one. I'm not going to go 2 times through the same code. Then I have this start pointer right here. This points to the very first element for the current argument. So at the moment it will just point to argbase, which is basically the address 0A. So now we start with the executable name. First we have this quoted variable here, which I set to false immediately, and then what I'm checking is basically the first character within the command line string, and I check if it is a quotation mark, because the executable name can be quoted or not. And in my case, it is actually quoted, so I'm setting quoted to true. Then we go down here and increment the base pointer by 1. So base will now be pointing to the character P. Now this while loop basically checks whether we encountered a 0 termination character, which means this is the end of the string. We do not have that, so this will be essentially true. And if we are in quoted mode, then we just continue with this loop again. Because we're pointing to P, we do not have a quotation mark, so we're going into this else block right here. And what's happening is we're going to increment the count by 1. So this means we now have one character that we need to copy into the output. We're writing the character P into whatever arg is pointing to. So at the moment it's pointing to address 0A, and then we advance the pointer by 1 after writing. So we point into the next free block of the buffer. Then we're just gonna increment base by 1 again. So we're now pointing to the character A, which means we can then just do the exact same thing. We increment the count and write the character A into the output. Then we increment the base again, point to character T, and we do this all the way through until we reach a quotation mark. So that will leave us with the path and myapp.exe into our argument buffer, and the count is 15. Now, because we encountered a quote, we are no longer in quoted mode, and we increment the base pointer by 1 again, so it points to the very next character, which in this case will be a space. Now, base is not a zero terminated character, and we are no longer in quoted mode, so these checks apply down here. The while loop would basically go as long as we do not encounter a space or a tab. Space or tab essentially denotes the end of an argument. So in our case, we have a space, so we know this argument is now done. Now, because we want to have zero terminated strings, we need to account for that as well. So we increment the count to 16 right here. And then I'm just gonna write the zero terminated character into the buffer. Here I'm gonna set the first element of the argv array into whatever the start variable is holding, which is the address 0A. And then I'm gonna increment argv after that, so it points to the next slot in the array, so index 1. So now index 0 actually points to the beginning of the buffer, mainly address 0A, which as you can see is the start of the path myapp.exe. Then we go into this while loop here. Again, there's a bunch of checks throughout. If it reaches the end of the string, the zero termination character, then we're just gonna give up. But at this point, we're just gonna continue into the switch, and we have a whitespace character right here, and then we're advancing the pointer by 1 again. As soon as we have a character that is not one of those two whitespace characters, I can be certain to have an argument. And indeed, if you see, we have character A, which is the start of the next argument right there. So I'm going to increment the argument count by 1. And then I'm also going to set the start variable to a new value, which is the address of argument at the moment, which is 4A. Now this basically means this is the start of the next argument. And then just to keep this code a bit clean, I have this command line end of argument function right here, where I just pass in the base pointer, the current count, and the argument that I'm pointing to. So let's jump into this function right here. So again, we're going to go into this while loop. We still have a valid character. In this case, it's character A. We're going to have a switch over it. And because it's none of these characters here, we're going to go into this default branch right here, which means it's a character that we just need to copy. So I'm going to increment the count by 1, and I'm just going to write A into the argument buffer right here. Then I'm going to point to the next character by incrementing base right here. So now we're going to go back into this switch, and this time we have a backslash character. So I'm going to jump into this function called command line end of backslash. Now, if you remember, there's special rules with backslashes. Any amount of backslashes followed by a quotation mark need to go through a special parsing rule, but we'll get into that. So first, what I'm doing is looping over all the backslashes to essentially count them. So we're going to the next character right here, which is still backslash, going to the next character, still a backslash, and then we're going to the next character, which is B. So we break out of this loop because there's no longer a backslash in there. Then I'm basically gonna subtract the starting address from the base address right here, and that gives me the number of backslashes. Now, this start is not the same start that I set in the main function, so this does not point to 4A, but rather pointed to the first backslash. Unfortunate naming right here, but please do not confuse these. So in this case, we have 3 backslashes. And then depending on whatever the character is after the backslash, I need to account for special rules. So if it is not a quotation mark, I go into this branch. And if it would be a quotation mark, I go into this branch. But in our case here, it is just a B. So we're going into this branch right here, which basically means we're just leaving the backslashes as is and copying them. No special rules are applied. So I can just add the number of backslashes to the count, which is 3, and then I'm just going to write out the backslashes into the argument buffer. And then basically I'm just going to return the base pointer right here, which means we're still pointing to the character B, so I can go back to command line end of argument. And then we're going through this loop, through the switch again, and into this default branch right here. Again, increment the count by 1, write out the character B, and increment the pointer. Now, because the next character is a space, we have reached the end of the argument, so we can just return out of here. So now that we have the end of the argument and copied all of the characters of that argument into the buffer, I need to account for the zero termination character, because again, we want every string to be null terminated. So I'm going to increment the count by 1 and then write the null termination character into the buffer. Now, the next item in argv, so with index 1, needs to point to the beginning of that argument a \\\\b, and we have stored this starting address into the variable start before, so for a, so we just now need to write that address into the array, and then of course we increment into the next slot of the array. Now we continue with this loop again, and because we have a space, we just increment to the next character, and then it will go back into this default branch. This means we have a new argument, so we increment the count and we set the starting address to wherever the argument pointer is at the moment. In this case, it is 5C. Then we go back into command line end of argument, which will bring us right back into this switch here, and this time we have a quotation mark. Now this means our entire argument is surrounded by quotation marks, and we do not write them out into the buffer, so they will also not be counted for the byte count in the end, which is why when I'm calling command line end of quote here, I'll increment the base pointer by 1, so it will essentially point to the next character, in this case C. So now I'm in command line end of quote, basically go over the switch. There's some special cases, so if it is a quotation mark, then it probably is the end, but it is not at the moment. It's also not a backslash, so we're just going to go into the default branch. It's just a character that we need to copy into the output buffer. So now we're going to go back into this while loop, still all valid, so we go into this switch case, and now we have a backslash, which means we're going to go into this command line end of backslash function again. And then we're just going to count all the backslashes until we have the quotation mark character again, right? So backslashes is still 3, but this time when we go into the space, it is actually a quotation mark, so we'll go into this else branch right here. And what's happening here is we need to figure out how many backslashes need to be written into the output buffer. Every pair of backslashes will just be combined as one backslash. It is basically counted as an escaped backslash character. And then we need to figure out whether we have an even number of backslashes or an odd number of backslashes. So we're just going to do that here with modulo 2, which means if the remainder is 1, then it is an odd number of backslashes, and if it is 0, it's an even number of backslashes. Now we're just gonna add the amount of characters that we need to write. Then I'm going to write all the backslashes into the output buffer. In this case, it's just 1. Because we have an odd number of backslashes, we have an escaped quotation mark, so we can just write it as a single quotation mark into the output buffer. And then I'm just going to advance the base pointer to the next character right here and return that address out of this function. So now we're in command line end of quote again, and as you see, because the quotation mark was an escaped quotation mark, the quoted argument is not at an end yet. So we again go into this default branch where we just have a single character that we need to copy, so we're going to do all that. So now we're pointing to a quotation mark again, which means we're going into this switch case right here. Now this is a rule I haven't talked about before when it comes to command line parsing, but every double quotation mark actually are an escaped quotation mark as well, and are just interpreted as a single quotation mark that needs to go into the output string. We have a quotation mark right now, so we need to look one character ahead, so we increment the base pointer, and then we check whether it is a quotation mark as well. And indeed it is. So that means we have an escaped quotation mark in our hands. So we increment the count by 1 and write a quotation mark into the output buffer, and then go to the next character again, which will bring us back into this switch case right here. So now this time we have a quotation mark and we need to look one character ahead, which we're going to do right now. and this basically points to the end of the string. And since the string is 0 terminated, this will just be the /0 character. So in this case, we're going to go into this if branch right here. So we're just going to return that address. And then we can go back to command line end of argument right here. So we have reached the last quotation mark. So we're going to go through this loop again, and this while loop will now terminate because we now point to the end of the string. So we're just going to return base right here and go back to parse command line. Now for the last argument again, we need to account for the 0 character, which means we're going to increment count by 1 again, and then we're going to write the 0 termination character, and then we need to write the starting address for this argument into the current argv array index. So in this case in index 2, and we're going to write the address 5c into it, because this is where our argument starts. Now we're going back to this while loop, and again it will terminate because we have reached the end of the string. Now I need to account for the null character, which is why I'm incrementing the argument count by 1 again. And then what I'm going to do is at the current position of argv, so index 3, I'm just going to write a null pointer. And this brings us out of the parse command line function. So, and what we end up with in the end is the following array. It has 4 items in there. Item 0 is pointing to address 0a, which is just path myapp.exe. Then we have the first index, which is pointing to address 4a, which is just a ////b. And then we have the second index, which is pointing to address 5c, which is just the string c // d . And then of course the last index, index 3 in the array, will just be a null pointer. Now that I implemented my own version of what the C runtime is doing under the hood, I would like to know if I might have made things slower by accident. Maybe the C runtime was doing something clever that I missed. In the very least, I would like to know how much worse my own implementation is. So I wrote a little benchmark that is parsing 10,000 single character arguments, which makes it roughly 20,000 characters in total because of the spacing in between them. I also added a benchmark for longer arguments, about 10 to 50 characters long, with a total of 32,000 characters. Then I had a mix of quoted arguments and a bunch of escaped characters in them. The string is randomized on every run, but it is shared between all implementations throughout the benchmarks, so there is no variance in between them. I copy-pasted the C runtime code into the benchmark and measured the runtime against my own implementation, but I only measured the counting and copying of the arguments, not the memory allocation in between them. But just for fun, I also included the Shell32 API into the benchmarks, but there was no way for me to remove, the memory allocation from the final result. And it's also a bit of an unfair comparison since it's also parsing UTF-16 strings instead of UTF-8. But I just wanted to add it for the fun of it. On the x-axis, I have the different benchmarks that I ran. On the y-axis, I have the amount of CPU cycles it took to run. 300,000 cycles are roughly 80 microseconds on my machine. The blue bar is the Shell32 Windows API, the green bar is the Windows C runtime, and then the gray bar is my implementation. At first I was a bit skeptical that my implementation was faster than that of the C runtime. I thought that maybe I missed something crucial, but as far as I can tell, my way of parsing is generating the exact same results. I think what might have helped was to add the argument and quotation parsing into separate functions, as opposed to having a bunch of if-else branches within the same loop, to determine the parsing state. So that gave me another idea. Calling the same method twice, once for counting and once for parsing, might be slowing things down a bit as well, because every time a character gets counted, another check has to be done to see in which parsing state I'm in and whether I need to copy that character as well or not. So in order to avoid those branches, I split up the parse command line into 2 functions instead. One of the functions is only for counting and the other is only for parsing. Looking at the benchmark results, you can see that it only added a slight boost. Probably not worth doing, but I kind of like the mental separation of concerns here. Having two different functions is easier to reason about, in my opinion. Anyways, I now have a way to emulate what the C runtime is doing, and I could go ahead and use argc and argv in all my applications. But I'm not quite happy with all the work that is involved to just get an array of arguments. Yes, on my CPU it's just a few microseconds in the absolute worst case, but this voice in the back of my head is just shouting at me to stop doing unnecessary work. So with that in mind, I would like to show you my way of handling command line arguments on Windows. I figured before I jump straight into the code, I'm going to show you how my algorithm works based on an example. Let's take this command line argument string right here. What I thought was, instead of iterating twice over it, I'm just going to have a single function that is called getNextArgument. So if I run this the first time, what it will return is an argument struct with a type of quoted to signify that this is a quoted argument, and then with a value of my path and my app.exe. Now, the quotation marks are included in this instance. Basically, I did not want to do some extra parsing to just leave them out. And what I'm then doing is, instead of copying all that data, I'm just modifying the original command line argument string, and I'm placing a null termination character as opposed to where the space is. So now basically value points to the same command line argument string, but because I have it zero terminated right at the myapp.exe, this value will never go further than that. Now if I call next argument again, it will return another argument struct with a type of short. So every minus character that I find signifies a short command line argument, and then the value will just be the A. And again, as before, I'm going to just put a zero termination character where the space is. If I call next argument again, it will return a type of long, because minus minus usually signifies a longer name. So the value will then be foo, because again, I put a zero termination character right there. Then if I call next argument again, I will get a type of Windows, because the slash signifies a Windows command line argument or something that is typical for Windows, and I will just return the X. And again, I will add a zero termination character to the original string. Then after another call, I will get a type of text, because this command line argument is not preceded by a slash, a minus minus, or a minus. Also, it is not quoted, so it's just a simple text. And the value will just be bar, and again, the space will be replaced with a zero termination character. And then after another call, I get the quoted value, and as you can see, I do not do anything special for the escape characters here, because to be honest, I do not really need that functionality, but if I would need it, I can then simply modify that data in place. And then because the string actually ends, I do not need to add a zero termination character because it will be already there. And if I call next argument, then I will just get a type of none with a value of 0. But if I modify the original command line argument string, any call to get command line would then just return the executable name, so I cannot use the APIs anywhere else in the program. But to me, that is not really a problem, because command line arguments are passed usually at the beginning of the program and just once. So let's just have a look at how my approach and the C runtime approach differs. First, it would iterate over the command line argument string and count all the arguments and characters. It would then allocate a block of memory on the heap for the argv array and the character data that needs to be copied. And as a third step, it would then iterate over the argument string again and then copy every single character and argument into the newly allocated buffer. Then if I want to interpret those command line arguments, I would then have to iterate over the argv array and then do my parsing and set all the flags that I need throughout the program. Now, compared to my approach, I have this first step of iterating over the argument string, and I immediately parse it as I go along and set all the necessary flags that I need. And that's it. I do not have to do anything else. So my approach is cutting down the work that needs to be done from 3 iterations to just 1, and from 1 allocation to 0 allocations. Now let's have a look at the code. So first I have this command line struct right here, which basically is just the pointer into the command line argument string. Then I have this init command line macro right here, which basically is just calling get command line A. Then I have an enum of all the different types that are possible. So none is for when we reach the end of the command line argument string. And then I have short, long, windows, text, and quoted here, same as I showed in the slides before. But this is just an example. You can basically add whatever type you would like. For example, if you would like to parse a number, add a number type. You basically just change this to whatever you need. It is similar to what a tokenizer would do. Then there is the command line argument struct, which holds the argument type. It holds the beginning of the value, and then I also have the length of the argument. Now, length is not strictly speaking necessary because I will zero terminate every single value, but I find it is nice to have the overall length in there for some quick checks. Then let's skip this function for now, and here we have the getNext command line argument function. It passes in the pointer of the command line. I also have the argument struct that needs to be filled out. So the first thing that's happening is I'm skipping all the white spaces. If we have skipped all the white spaces, there will be a valid character in there or a zero termination. So I'm trying to determine what kind of argument I have. So this basically sets the argument type. So if it is a null terminated character, then of course we have reached the end of the command line argument string, so we just return argument type none. If it is a minus, I'm gonna look ahead 1 character to see if there is another minus. Now, if there is another minus, so a minus minus, then it is a long argument type by convention. And if it is just 1 minus, well, then it is a short argument by convention. Then I have a slash character for Windows type arguments. I have a quotation mark for quoted arguments. And then if it is none of these, then it will just be a text argument. So here I'm setting the argument base. Then we go into the while loop here, where we basically parse all the characters until we reach a whitespace character right here, in which case I'm gonna write the null termination character into the original string right here. So if it is a quotation mark, I'm going into this count command line quote, similar to what I have done before. So this is just the function up here, where I'm basically just iterating over all the characters and increase the character count for the length of the argument right here until I reach a quotation mark. Anytime I have an escape character, I'm just going to ignore the character right after it. So I'm just looking for a quotation mark right here. Then I have slashes, which are not in a quoted string. So in this case, I'm just gonna try and ignore the next character that comes after it, or if the next character after it is a null termination character, a space, or a tab, I'm gonna write the null termination character right here. And if it is a null termination character already, I'm just going to return. And then if it is anything else, just increase the argument length by 1 and go to the next character, and then just do this over and over and over. So this is how you would use it. Program start is my main function essentially. So what I'm doing here is I have the command line struct right here and call the init command line macro. This will fill in the base of the command line. I'm also printing it out. Then I basically have this do while loop where I'm just checking the argument type. Now, if the argument type is none, which equates to a 0, this while loop will terminate. So, and then I'm just calling getNext command line here, passing the command line, passing the argument to fill in, and then have this switch based on the type of the argument. So if it is a short, I'm printing out short argument. If it is long, I'm printing out long argument, and so on. So I'm basically printing out all those different values. And if I run this now, you can see it prints out the command line argument string right here with the executable name. And then I get a quoted argument, which is the executable name right here with quotation marks included. Then I'm getting a short argument of value A, long argument of value foo, window style argument of X, and a text argument of bar, and then the quoted argument right here. And as you can see, we do not do any special work right here. So these escaped quotation marks and escaped backslashes basically just remain the same. And then I'm getting a none token, which just indicates the loop is done. And of course, I also added this way of handling command line arguments into the benchmark, but keep in mind, I'm doing a lot less work when it comes to string parsing, so this comparison is also a bit unfair. But I still wanted to know, where it would end up runtime-wise when compared to the other implementations. And that is how I handle command line arguments in my own programs. Well, I'm always changing a few things here and there depending on the requirements, but it is essentially the way I'm doing things. Let me know down in the comments what you think about that. And again, this is only useful for native Windows applications or programs that do not link against the C runtime on Windows. And of course, if you require wildcard expansions in your program, you probably have to take a whole different approach to this whole command line thing. I'm not quite sure because personally, I never needed to use them, so I haven't looked into this whole area of how to even handle that. Anyways, I hope this was somewhat useful and interesting to you. This video took me a lot longer than I expected it to take, mostly because of all the animations and the explanations. So if you like this format, please let me know down in the comments, but I'm not sure all future videos will be like that, but that's probably something I could talk about in a vlog or something. Anyway, that's it. Bye for now. Thanks for watching, and I see you next time.